You know the statement of maximum power transfer theorem? What is the statement? Can you recall? So maximum power transfer theorem states that maximum power will be transferred to the load. It's related to power which will be transferred to the load. So maximum power transfer to the load when it will be transferred? Will be transferred to the load when load resistance is equal to the Thevenin's equivalent resistance. Or you can say that source resistance also. Okay. So here we are talking about the DC circuit. So that RL should be equal to RTH. In case of AC circuit will have load resistance should be conjugate of the source resistance. Now here they are asking we have to prove that maximum power transfer theorem. So we have to derive the condition where we'll show that when RL equal, that is load resistance equal to Thevenin's resistance, then maximum power will be transferred. For that, we are considering a small circuit here. So in this, we are considering the Thevenin's voltage, okay, as well as Thevenin's resistance, and here we have load resistance. So this is plus minus, this is our VTS, Thevenin's voltage, this is the RTH, and this one is the load. Now here we'll see the condition when maximum power will be transferred to the load. So for that, first of all, here we have to find the what will be the current here, okay? So that current, if we try to calculate, so what will be the value of I? I will be given as VTH by RTH plus RL. And if you see that power in terms of current and resistance, that is the power at load resistance you will try to find. So PL will be equal to I square into RL. So same current is going to flow through the load resistance also. So finally, from here, we'll get PL. So that value of I we are going to substitute. So BTH by RTH plus RL, this entire whole square into RL. Okay. So finally, this side, if you simplify, we'll have BTH whole square divided by RTH plus RL whole square, and it is multiplied by RL. So this one, suppose we'll consider this will take as the equation 1 and this one as the equation 2. Now, if you know that if you have to find the maximum or minimum value, so then you have to differentiate the expression and you have to equate to the 0. So that's why we are going to differentiate equation 2 with respect to RL. It is the function of RL here. After that, we are going to equate and we'll see that condition how we are going to get. So finally here, we are going to take derivative of this load resistance with respect to load resistance. This should be equal to 0 for the, so here we are looking for the maximum condition. So for the maximum value. So now finally we'll go for the derivation of this. So when we are going to differentiate, so we have dPL by dRL equal to, so now you see that BTH square will be constant, so that is kept aside. And here we will use the U by P, that property of the derivation, where how you are going to derive, how you are going to find the derivative when we have in this expression in the form of U by P. So you are aware of that, that will be B into du. Okay, so B is the denominator part here. Okay, and U is the RL. So RL derivative is RL is the 1 minus again U into B. So that is the 2 into derivative of this B, RTH plus RL. Again, this back to RL. So this is the 1 here for this case. And overall, it is being divided by, that is the B square. So we have here RTH plus RL whole square, and again this is the square. So if you're able to remind in the school days, you have derivation of this one. So suppose we have some expression in the form of U by V. Okay. So that you are going to do V du by dx minus U into dB by dx. Okay. And overall divide by B square. So that concept we are using here. So finally, this one we are equating to 0. So after rearrangement of all these things, again we have to apply the square inside this bracket. So finally, what we'll get here? This dPL by dRL equal to BTH1 means we can say in that side. Okay. So now this expression we have finally, we'll apply the a plus b whole square. So RTH square plus RL square plus 2 RTH into RL. And inside that, now you can expand this one. So we'll get again 2 RTH into RL minus 2 RL whole square. And here in the denominator, we'll have RTH plus RL to the power whole 4. 2 into 2 here, power is the 4. So finally, if you see that what are things we can cancel here, this term is going to cancel. So finally, you'll get here BTH square, and here inside the bracket we have RTH square, and here this RL square minus 2 RL square. So you get minus RL square here. And this is overall divided by RTH plus RL to the power 4. Okay. So finally, this one we have expression that is the a square minus b square. We have BTH square, and you'll get here RTH plus RL into RTH minus RL, and this overall is divided by RTH plus RL to the power 4. So finally, this RTH will be cancelled, one RTH from here, so we'll get here power 3. Okay. So this one finally, if you see that, we'll have expression dPL by dRL equal to BTH square into RTH minus RL divided by RTH plus RL to the power 3. Okay. So now in this case, what will be the condition? This is going to be equal to 0. So when it will be equal to 0? So if you're seeing that here denominator is positive RTH plus RL, and it is the cube, and numerator is only what we have RTH minus RL. So if this RTH minus RL is going to be equal to 0, then only it will satisfy the condition that derivative of PL with respect to RL is going to be equal to 0. So that's why if RTH equal to minus RL equal to 0, then what we'll get here from here? That is RTH equal to RL. So this is the condition when maximum power will be transferred to the load. Okay. And already we have expression earlier, and again you can write, so that maximum power transferred to the load will be the condition PL max, that we'll have here BTH square into RL divided by 2 RL whole square. So here what we are doing in the equation 2, in place of RTH we are writing the RL, or you can in place of RL you can write the RTH. So in the both case, your expression will become here BTH squared by 4 RL, or you can write BTH squared by 4 RTH. So this is the maximum power transfer theorem, the condition is that RTS should be equal to RL, then only maximum power will be transferred. Thank you. Like, subscribe, and